You all there? Sorry, it took me a little bit extra. You guys there? Anybody there?
I'm listening.
Okay, all right, I just want to make sure you're there. Okay, so just recap, you folks did the multimeter quiz and you're working on Ohm's law. And I did lecture through parts of chapter 27 already. Ohm's law, if we have a circuit with a battery and a resistor, basically if you plot current here, the potential you apply to the resistor on the horizontal axis, you'll get a horizontal, not a horizontal line, a straight line if you vary V and measure I. If a material obeys Ohm's law, you will get a straight line. Okay? That means that the ratio of delta V over I stays the same, independent of the applied voltage, the applied potential difference. Okay? And so any material that obeys this equation, independent of the applied voltage, or let me rephrase that. Any material that obeys this equation, and R is constant independent of V, obeys Ohm's law. And resistance was measured in ohms. And then the symbol for it is the capital Greek letter, the Greek capital letter omega. Okay. I haven't really shown you what a resistor looks like. Well, or different examples of resistors. So let me show you different examples of resistors. There's a lot more than what I'm going to show you here. A resistor is basically a device that's used to limit current. So there's a bunch of them here in a circuit. Okay. There's one that's wire wound, and here's another one that's wire wound. There's a bunch of them here. 1, 2, 3, 4, 5 resistors here. This device is called a rheostat. It's a variable resistance. It's used for high current applications. This is the old one. And you slide this to vary the resistance. Well, it's tough to slide. Okay, they're devices that are used to limit current or give you a particular voltage drop across it. Okay. And these devices are designed to obey Ohm's law as long as you're not putting too much energy in them. The size of these kind of resistors, these are carbon resistors. And you have much smaller ones in your lab kits. They're indicative of how much power they're rated for. If you put too much, if you go above that power value, these things will heat up and they won't obey Ohm's law anymore. Okay. Light bulbs don't obey Ohm's law because R changes as you change the voltage. And you're going to see that in the lab you're going to work on. Okay. So this is what we talked about for the multimeter quiz. And then we also discussed the various aspects of a circuit we talked about the fact that the power supply, or your battery, has an internal resistance. And when we draw a power supply with an internal resistance, we generally add a resistor to the circuit. That's squiggly line again is that symbol for the resistor. Okay? And we put a box around it. That whole box represents the actual power supply. Because of the internal resistance, the voltage, let me change the size of this. The voltage across a load, across any resistor, is not called EMF, but it's called a terminal voltage. And it's less than the rated voltage because of that internal resistance. And when we're analyzing circuits, we're going to assume that the wires have negligible resistance compared to the resistor or your load. Here's another picture of the building blocks of a circuit. This one has two resistors in parallel. Each complete path, closed path, is called a loop. This circuit shows really three loops, and any of those three loops can be used to analyze the circuit. Where you see the red dots, where the current can take more than one path, those are called nodes or junctions. And we did
So, Professor,
yeah.
go back one slide. So you said three loops, so it could go around in a loop on just the top?
Yeah, the top loop with just the two resistors?
Mm-hmm.
Yeah, that's a complete path. I mean, and I know there's no battery there, but we can still use it to analyze
Just
the
like
circuit.
just like going in a circle without the going back to the battery?
Sure, sure.
Okay.
And then there's the outer one too.
Yeah.
Yeah, any one of those can be used. And the reason why is because we know, I mean, really, there's an electric field in the wire, right? This is causing the electrons to move. So if you integrate the electric field around the loop, because the electric field is conservative, right? If I integrate around a closed path, any closed path, I should get zero. So I can use that idea to solve circuits. We'll see that later on in chapter 28. But that means that the voltage drop across the two resistors that you see there in that top loop they're equal. And of course that's obvious to us because they're in parallel to each other. That make sense? That idea is not going to be that important in this particular circuit, but in more complex circuit, it's going to be an important idea. The fact that we can use any of those loops to analyze a circuit. Okay, so what I want to do now is really talk about just a model for electricity, for charges moving through a wire. When you connect a light bulb to a battery or a power supply, the battery does work on the electrons, giving them kinetic energy. The kinetic energy gained by the electrons is actually lost by them because of the fact that these electrons are colliding with the atoms in the wire. After every collision, energy is lost by the electrons. That energy is converted into heat. In the case of a light bulb, the filament gets hot enough so that it glows. So if you ever use a high current device, like a drill or, trying to think of, anything that uses a lot of current, vacuum cleaner, you can feel that the wire gets warm after using it for a while. That's because the electrons are dumping their energy into the material. And then that energy goes into the vibration, increasing the vibrational energy of the atoms in the metal. And the material warms up.
Makes sense.
So I want to just talk about a simple model. And the reason why I say it's simple, it's because of the fact that we're not taking into account quantum mechanics, which we want to do, okay? Not at this level. So let's say we have a wire. We can just focus on a wire. We don't have to focus on the whole circuit. So here's a wire. And of course, the charge carriers in the wire, they're going to be electrons. We're going to apply a potential difference across the wire. Since you have a potential gradient across the wire, that means you have an electric field. Let's focus on one of the electrons that's experiencing this electric field. We know from Newton's second law that the net force, if we sum all the forces acting on the electrons, and here we're going to assume all the forces are just those due to the electric field, that the sum of all the forces is going to be equal to ma. And then A is going to be Q E over M.
Is that a sigma at the beginning?
Yeah, summing all the forces. Sigma of all the forces. Right. That's how we usually write summing the forces. So let's sum all the forces on the on any electron. Let's pretend there's only really one force, and that's due to the electric field. Okay. The sum of all the forces gives you the net force, which is Q times E in this case, and that's equal to ma according to Newton's second law. Solving for A gives you QE over M. Of course, this is dV dt.
Where v is velocity, right?
Right. So if we solve for V by integrating, then I get the integral of dV equals the integral of A dt. So this is going to give me a constant of integration. And that constant of integration is my initial velocity. We're assuming here the electric field is uniform. And it is when we're using a battery like this. Okay? So this is the velocity of any electron given the acceleration of the electron. Of course, this is an approximation because the electrons, as they go through the wire, they're colliding with atoms in the molecule, and they're probably interacting with each other. So there is a repulsive force between the electrons I am ignoring here. But again, I'm making a very simple model. I want to look at the collective motion of all the electrons. Based on this model. I want to calculate the average velocity of all these electrons. I want to find the average of this for all the electrons in the wire. Well, if A is uniform, the average of A is A. Okay. Now, what is the average of this thing, the initial velocity? If I have wires, a whole bunch of electrons in a wire, the initial velocities of all the electrons are pretty much random. If you average out vectors that are randomly oriented, what are you going to get? You're going to get 0. So this ends up being 0. And then V average is equal to A times some effective time, I'll call tau. And I'm going to approximate this, because I don't know what this value is. I'm going to just use it as the time between collisions, or the average time. I really don't know what the collision time is. So I'm just going to say tau is the average time between collisions, between the electron and some atom in the metal. Okay? So this V average, I'm going to call it the drift velocity. And I want to see what I can learn from that. When we did this multimeter, when we did the multimeter discussion, I described I as N Q V drift times A. I now have a theoretical expression for a V drift. Well, it's a model. I mean, it comes from a model. Okay. I want to look at the amount of current per unit area. We call it J, but J is really a vector. I'll say something about that in a little bit. I want to look at the amount of the number of coulombs per unit area. And really, this is the magnitude of a vector, because this is a vector that's the current per unit area in a particular direction. This basically represents the flow of charge per unit area. And so this is really the magnitude of the drift velocity. Well, if I put in my expression for the drift velocity, then I'm going to get but of course, A here, this A is QE over M. Okay, that A is QE over M, so I can put that also here. So this gives me N Q squared over M times tau. Let me rearrange this a little bit. This is I over A. And this is called the magnitude of the current density. J is the current per unit area. So what does this depend on? It's basically some constant times the electric field. So J is some constant times the electric field. This whole thing is a constant. I don't know if you remember, this is the number of charge carriers per unit volume. This is the value of the charge, which is in this case going to be the electrons. And that's the magnitude of the drift velocity. So basically, the current depends on the electric field. The current density depends on the electric field. It's proportional to. Okay? I'll write it over here.
On the slide, it has M sub E, I think. Is that?
Yeah, that's
like
the mass of the electron.
Okay.
I've been focusing on the mass of the electron, but then you can do this in general too. I mean, I could put an MCB here. I mean, but isn't it true then I can apply this to any charge carrier? Like if I was doing chemistry and I was doing electrochemistry, the charge carriers might not be an electron. It could be some sort of ion in this chemical solution.
That makes sense. I was just curious.
Yeah.
Than
No, but you're right. I mean,
correct.
maybe I should just be consistent. I'll put the E there. And so this is a constant. I is proportional to E. J is proportional to E. Okay. Let me say something about J. J represents just a flow through a flow through a surface. We talked about that with the electric field. The integral of J dot NdA is the flux of charge going through a surface. Okay, it's called the current density. And it is a vector. And its direction is the same as the drift velocity. Okay. Now this relationship that J is proportional to the electric field, this constant is called the conductivity. So define NQ squared over M sub E tau as sigma. It has units of amps per voltmeter. Okay. If you take the ratio of J over E, you get sigma. And for many materials, this ratio is independent of the applied electric field. It's independent of the applied potential difference between the ends of the wire. This is Ohm's law. This is a material that obeys Ohm's law. All I got to do is throw in an area and some other terms, and I have a voltage and a current in here. Okay. This is just missing some geometrical factors, and I have Ohm's law, how we wrote it before. So this is Ohm's law. From a very fundamental point of view, it's the ratio of the current density over the electric field. Okay, and Ohm's law is like Hooke's law, is that it's only valid for a certain range of E's. Like, remember, Hooke's law is not always valid, right? If you take a spring and you stretch it too much, Hooke's law is not valid anymore. Okay? Now, since E is constant, let me draw my wire again. Let's say this is the length of the wire. Since E is constant along this wire, then delta V, its magnitude, is equal to the electric field times L. Then J, this J, is going to be the conductivity. This is sigma, remember, times delta V over L. So let me erase the board and rewrite some things. Now, let me write this in terms of delta V. Let me solve for delta V. What do I get? Delta V is equal to L over sigma times J. Now I'm going to multiply numerator and denominator by A. J times A is current. This thing over here is called a resistance. So just multiplying numerator and denominator by A gives me Ohm's law that you're familiar with. So we can actually kind of model Ohm's law. You can see where this comes from. Okay, and R is called a resistance.
At the top of the wire on top, is that an equal sign or a minus sign?
This up here?
Yeah.
It's an equal sign, sorry.
Okay, that's okay. Just me.
So define rho as equal to 1 over sigma. So then delta V is rho L over A times I. So resistance then is rho times L over A. So 1 over the conductivity is called a resistivity. And the units are ohms times meters. This is a property of the material. This represents a resistance the material has for current. I'm sorry. to the flow of current, to the flow of charge, resistance to a flow of charge. Or you can say resistance to current. Okay, it's a property of the material, rho is. R is not, because R depends on L and A. So this is the second quantity we are learning this semester that depends on geometry. Okay, the fact that R is rho L over A, this depends on geometry and something that involves the property of the material, rho. In the case of capacitance, the property of the material was the dielectric constant times epsilon naught. Here it's the resistivity. And here, the thing is in our model, this is a constant. Remember, 1 over this is the resistivity. Here in our model, this is a constant, but in reality, it's not. This model does not take into account quantum physics and the electron-electron interactions. This term does depend on temperature in reality. But our still simple model, it's called a Drude model, allows us to see the relationship between V and I, at least from a simple point of view. The only thing it doesn't get right is this thing. Okay? So if you take the ratio of E over J, the magnitude of E over the magnitude of J, that's the resistivity. Now for conductors, the resistivity is like 10 to the minus 8 ohm meters. And for insulators, it's about 10 to the 10th ohm meters. Those are just ballpark figures. Now, over a limited temperature range, this resistivity depends linearly on temperature. I'll say that again. For a limited temperature range, this quantity, the resistivity, or 1 over the conductivity, is linearly dependent on temperature. In order to really get a good value for rho as a function of temperature, you actually have to do an experiment. Of course, the experiments have been done. You actually have to look the information up in a table, because it might be a straight line. The graph of rho as a function of temperature might be a straight line for a small temperature range, but beyond that temperature range, it's going to have a complex function. Or I should say complicated function. I've got to be careful with the word complex. So over a limited temperature range, and we know this from experiment, okay? I'm not going to derive anything here. Rho is equal to rho naught times 1 plus alpha T minus T naught. Well, rho naught equal resistivity. Generally, it's at 20 degrees Celsius. And T naught is generally 20 degrees Celsius. I mean, this is not even constant. This is the coefficient of resistivity. I don't know if you've taken 215 yet, or anybody who's talked about thermal expansion, you've seen an equation very similar to this. Okay. And so then, if this depends on temperature, then R depends on temperature. So if you have a material that does not obey Ohm's law, whose resistance depends on temperature, you can use that resistor as a thermometer. As long as you know R at any temperature, then you can actually use that resistor as a thermometer. And they do it with platinum. If you solve this for alpha, and this alpha is just an average value, is 1 over rho naught times delta rho over delta T. Or if you want to know, in the limit as delta T goes to 0, then it's a derivative. I don't spend a lot of time on this. There's like 1 or 2 homework problems on this, but I really don't spend a lot of time. This is more of an engineering consideration, and so when you take engineering courses, you'll deal with this more. It's a property of material you got to learn how to deal with. If you're designing a circuit where you have to understand the change in resistance as a function of temperature. Okay. Devices that are used devices that are used as thermometers where the resistivity or resistance changes, they're called thermistors. One of the things that you need to remember and understand, and people forget, is that a conductor that obeys Ohm's law, the resistance of the device is independent of the magnitude and polarity of the applied potential difference. R is a constant regardless of what delta V is. Okay, that's something important to remember. I want to say one other thing about the drift velocity, which I erased. This represents the average speeds of the electrons going through the wire. How big do you think that value is? Just guess.
Like how big, or guess how big?
Guess how big the drift velocity is for the electrons in a wire.
Not very big, or
Yeah, you're
I'm
right. It's
thinking
not very
like
big.
10 to the negative something, 10 to the negative 10 or 15 or something.
Well, maybe not that slow, but
Okay.
because it would take centuries for the electrons to go through the wire. If
Oh,
that's the
yeah,
case.
yeah.
But it's like the velocity of a crawling bug. It's in less than a centimeter per second.
Okay.
And so the question is then, aren't the electrons moving fast in the wire? The answer is yes, but they're also colliding with other atoms in the wire. So even though they may be moving very quickly in the wire, if you take the distance divided by the total time it takes to go from one end to the other, it's actually a small value. Because we're talking about an average value, right? Based on all the collisions it makes.
Yeah.
And so it takes actually a long time for an electron to get through, even though in between collisions it's moving fast. So one question to ask is, well, if the electrons are moving slow, then why is it that if I can turn the light on, the light will go on before I jump into bed? The light goes on so fast when I flick the switch. Can't I just turn the light on, jump into bed, and then the light goes on? Why does the light go on right away?
Isn't it just because of all the collisions, so it kind of transfers the charge, or?
Well, the electrons are always there, right? Let's say you have a
True.
hose.
Yeah.
Let's say you have a hose full of water. You turn on the hose, the water comes out instantly, right?
Mm-hmm.
So the electrons are always there. So once you turn on the power, you have charge moving. If you had an empty hose and you turn on the water, then you have to wait a while for the water to go through the hose, right?
Yeah.
But when the water's full, you turn on the water comes out immediately. Same thing with the light switch. You turn on the light switch, the electrons are already there, so bang, the light goes on.
Yeah.
Once they start moving, then you have light.
Mm-hmm.
So I want to introduce to you one more concept. It's very important in this unit is electrical power. Now, remember the battery converts chemical energy into kinetic energy of the electrons. And this energy is lost as the electrons go through the wire. And you can see that because if you turn the switch off, if you remove the battery, the electrons start moving immediately. Okay, the light goes off. So as delta U decreases, that energy goes into the resistor. I think I have a mistake in my notes. So we want to look at the rate at which energy is dissipated in a circuit or any circuit element. And that's called power. Power is dW dt. The work done in moving a charge is just going to be delta V times dQ. Because you're moving a small amount of charge, dQ, over delta V. I want to know what it is per unit time. Delta V times I. So delta V times I is the power. This is a definition. It's not a special law. Okay, so delta V times I is power, and the unit is the joule per second, or the watts. All right, your light bulbs are rated in watts, right? Aren't your light bulbs rated in watts?
Yeah.
Yeah, and so that tells you how much energy per unit time is being used up by the bulb. Okay, and it's basically delta V times I.
How do you differentiate work, like symbol-wise, work from watts?
Well, work is watts times time. It's work. It's power times time. Or
No, I mean like the W. You use a different kind of form of a W for watts versus work, because they're both a W when you're abbreviating them.
well, I'm writing this in the units, right? I usually write this after the number,
Okay.
right? So the W, when you write the W after the number, that's watts.
Okay.
But you don't put the W for work after a number, right?
True. Yeah.
Okay.
Good point.
So which has a greater resistance, a 25-watt bulb or a 100-watt bulb? So this question is actually getting old, because this is based on the old incandescent bulbs. All the bulbs now are LED. So the old incandescent bulbs, they still sell them. If you go to Home Depot or Lowe's, you'll find them. What are they rated? You know what a regular incandescent bulb is rated at? What voltage is
Rated. Oh, isn't it 130 or 120?
120, yeah. So bulbs, incandescent bulbs, are rated at 120 volts. So when you look at a bulb, an incandescent bulb, and it says it's 25 watts, that's 25 watts at 120 volts. Okay? Now, let's take a look at this equation first before I go on. This delta V times I. Remember that Ohm's law, delta V is I times R, and I is delta V over R. So I can write this a bunch of different ways. I can eliminate the I. I can take this and stick it in here and I get, or I can eliminate the V using this equation and I get, so I can write the equation for power three different ways. And I want to say something that's kind of a pet peeve of mine that people in other fields do, not really science fields, okay? They call this Watt's law, But it's not a law, it's just a definition. Power is a defined quantity. But some other fields will call this a law, and they do that because that helps the students remember. Okay? You will not see the term Watt's law in any physics book or in any electrical engineering book. But you'll see it, in courses like carpentry or whatever, where people are learning how to use. They need to know a little bit about circuits. They'll call this Watt's law, but it's not really Watt's law. That's just a way to make the people remember these equations. But it's not a law. It's power. Power is a definition. So let's go back to the question. Which bulb has a greater resistance, a 25 watt bulb or a 100 watt bulb? Since they're both rated at 120 volts, which form of the equation should I use to understand this? I think I'm going to use this one because the delta V is the same in both cases. So my power is delta V squared over R. So in one case I have 100 watts. In another case, in which case is the resistance higher? This one or this one?
Isn't it 100?
You're saying this one has a higher resistance than this one?
No, sorry, the 25 has.
Okay, all right, yeah, because this is a smaller number, the denominator.
I was thinking 25 times R is smaller than 100, but yeah.
So this has the higher resistance. The smaller the power rating, the greater the resistance. I'm going to do a demo next time. Remember this. The next lecture, I'm going to do a demo, and you have to know what this is. I'm going to have a bunch of incandescent bulbs, and I'm going to put them in a circuit. Okay, but I hope that more than 2 of you show up the next lecture.
Maybe we'll get 3 again.
Yeah. Okay. So let's do just one simple example, and then basically be done with this chapter. Oops. It's weird. I have 2 screens. That slide you see looks good in your case, but on my other screen, the resistor is invisible. Okay.
I wonder if that's because it's purple. But
yours looks purple?
Yeah, it's kind of a pink purple, so I don't know if that's why it's different on your screen, but I don't.
It's not there at all. Neither is
the voltmeter or amp.
No, the ammeter is there. Yeah, just the resistors is missing in my other screen. It's very strange.
Mm-hmm. Yeah.
Okay, so let me draw the circuit. So we have a 45 ohm resistor in a circuit. We're going to be measuring the current. Oh yeah, by the way, one of the big errors I saw in the multimeter quiz was students putting the ammeter in parallel. Never do that. Luckily, the 10 amp scale on our multimeter is not fused. Okay. People were putting the ammeter in parallel to the bulb. And of course, when you do that, the bulb goes out because all the current is going through the ammeter. Okay. And even though the bulb went out, people didn't notice that. Anyway, the battery voltage is 9 volts. And this is 45 ohms. I'll do a demo talking about that real quick on Friday. All right, so we want to calculate the current through the resistor, which is also the same as the current in the circuit because I only have one resistor in my circuit. The power dissipated by the resistor, the Q delivered by the battery, and the energy in kilowatt hours supplied by the battery in 15 minutes. So let's get I. Well, we know that delta V is I times R. So I is delta V over R. The potential difference across the resistor is the same as the battery voltage because all I have is the one resistor. 9 volts over 45 ohms. Remember, an ohm is a volt per amp. That's going to give me units of amps. This is going to be 0.20 amps or 200 milliamps. The power, P, can be calculated a lot of different ways. But since I know delta V and I know I, and this is the usual form, I'm going to write P this way. So this is going to be 9 volts times 0.2 amps. What is that going to give me? 1.8 watts. Okay.
Okay.
Let's calculate delta Q. How much charge is delivered by the battery? Well, I is dq over dt. And I is constant. dq is I dt. I integrate this, and I get delta Q is I times my time interval, delta t. Delta t is 15 minutes. I got to get that into seconds. How many seconds in 15 minutes? Let's see, 60 seconds per minute. 900 seconds. So this is going to be 0.2 amps times 900 seconds. An amp is a coulomb per second. The seconds cancel, and I get 180 coulombs. Okay. If you have a car battery, you can figure out how much charge your car battery can deliver based on its ratings. They'll be rated in amp hours. An amp times an hour is charge, but you got to convert the hour to seconds, and then you can see how many coulombs it can deliver. Okay, now we need power. We need the energy. Well, power is dW over dt. I'm going to do the same thing again. Power is constant. If I integrate both sides, I get the work done by the battery, which is the energy delivered by the battery, is P times delta T. The power is 1.8 watts. Times 900 seconds. And let's see how many joules this is first. This is 1,620 joules. Okay. We're going to convert it to kilowatt hour. What's a kilowatt hour? It's a unit of energy.
Professor?
Yeah.
Why is it not delta W
The change
at the
in
beginning?
work? Because
Just because it's an integral, so.
yeah, basically because this is 0.
Oh, okay, that makes sense.
Right? I mean, it's just a total work done.
Yeah.
It's always relative to 0.
Okay, yeah, that makes sense.
So 1 kilowatt hour is 1,000 watts times the number of seconds in an hour. So it's 3.6 times 10 to the 6 joules. So I got to divide this by 3.6 times 10 to the 6 joules per kilowatt hour. And that'll give you 4.5 times 10 to the minus 4 kilowatt hours. Now, if you know how much you're getting charged per kilowatt hour, you can figure out how much that costs you. That's how you look at your electric bill. Okay. Now, one other thing we can look at, the battery is 9 volts. So this is 9 joules per coulomb. It delivers 9 joules per coulomb, and it delivered 180 coulombs. If you take the 9 volts times 180 coulombs, you end up getting this 1,620 joules. So that's another way to calculate the energy delivered by the battery. Okay? So most of the homework problems are kind of like this, except there's one or two where you look at the temperature dependence of resistance. And then there's a bunch of multiple choice questions on the assignment to get you to think about how the electrons are going through a circuit. Any questions on this topic?
Not currently.
Okay. So that was it for 27. There's not much to 27 to me. I mean, this is it. The only other thing is one can do calculations of, calculating resistance for various geometries. And you see those in some books, but then there's some dispute as to whether those calculations are done correctly. So we won't do those. All right, so let's move on to chapter 28. And I'm going to spend most of the lecture next week on chapter 28, and it might even spill over to the following week. So we've talked a little bit about circuits. Basically, a circuit, basically something where you just have one resistor in it or one bulb in it, and that's it. So now we're going to start building more complex circuits and analyzing them. We're mainly going to focus on resistors, but then at the end of the chapter, we're going to throw in a capacitor. When we throw in a capacitor, the analysis is really not that hard, but students tend to have difficulty doing the RC circuits, even though they're pretty straightforward. You have to understand Kirchhoff's laws from really a fundamental point of view. Okay. So today I'm just going to focus on series and parallel resistors, and I'm not going to have that much time to do series and parallel. Okay, but I'll have a little bit more time next time. I'm just going to introduce you the equations for series and parallel. And my analysis is going to be very similar to the analysis I did for, oops, I forgot to do something, sorry. The analysis is going to be very similar to what I did with the capacitors. So just give me a second. So what I want to do is I want to look at a circuit with 2 resistors in it. We did a circuit with 2 capacitors in it. The circuit with 2 capacitors is very boring. And the reason why is because once the capacitors are charged, there's no more current in the circuit. Now the electrons stop moving. Capacitors are charged. Each capacitor has a certain voltage drop across them, and that's it. You're done. Nothing's going to change. But in the case where you have two resistors in your circuit, charge will still be moving. The current will be constant because you have your battery voltage is constant, your power supply voltage is constant. Okay? But you'll still have electron flow. So let me draw two resistors. These can be two light bulbs. Even though the light bulbs do not obey Ohm's law, they still obey the equation delta V is equal to I times R. This is still true even for light bulbs, even though they don't obey Ohm's law, because R is not constant for an applied delta V. As V changes, R will change, but this ratio stays the same. Or not this ratio, this equation stays the same. All right, so these two resistors are in series, just like the two light bulbs were in series in the multimeter quiz. So let's think about the electrons moving through this circuit. The electrons go this way, like so. The electrons only have one path, right?
Yeah.
Okay, so whatever goes through here has to go through here.
Yeah, they're in series.
They're in series. So whatever goes through here has to go through here. So they're in series. That means that both resistors have the same current. And again, we're using the letter I for current. By the way, one thing I forgot to mention, when you have a battery, the current is always in the same direction. That's called direct current. Okay. Even if it's not constant, as long as it's the same direction, we have direct current. Okay, so if this is let's say this is a 1.5 volt battery. So you have a potential, so the potential here is 1.5 volts, potential here is 1.5 volts, and the potential here is 0 volts because here it's 0 volts. So there's a voltage drop of 1.5 volts from here to here. Over here, the voltage is some intermediate value. Because what happens is you go through a resistor, you have a delta V across the resistor. Okay? Any resistor, you have a delta V through it, and that's because of this equation. So this is one voltage drop, this is another voltage drop. The sum of those two voltage drop has to be equal to the power supply voltage. So let's say we'll call delta V sub S the power supply voltage. This must be true because each one of these has a voltage drop because they obey Ohm's law. And you have the same current through both of them. If I want to replace those two resistors with an equivalent one, that provides the same current, how big is this resistor? Well, the equivalent resistance is R1 plus R2. If I had 3 resistors, then there would be a sum of 3 resistors. If I had 4 resistors in series, there would be a sum of 4 resistors. So in series, They just add. Notice, compare to the capacitors in series. Why is the relationship different? Because for the capacitor, delta V is Q over C, but for a resistor, delta V is I times R. The geometric factor, the resistance here is in the numerator, here it's in the denominator. Okay? So capacitors in series add like 1 over C1 plus 1 over C2 plus 1 over C3, and then you take the reciprocal of the whole thing. But resistors in series just add. They add like capacitors in parallel. Okay? And I have the derivation in your notes. And guess what's going to happen with resistors in parallel? That's a good question. Okay. Let me say something about the resistors in series before I talk about resistors in parallel. If I sum the voltage drops all the way around the loop, I get 0. Because this goes to your question, Scott, you asked earlier. It's going to be important when we analyze more complex circuit. Let's say this is 1.5 volts. Let's, for fun, just call this 1 volt, okay? All right, just for numerical sake. I'm going to go around clockwise and just add up all the delta V's. So 1.5. So it drops here, right? It drops by half a volt here.
Yeah.
So it's negative a half, right?
Mm-hmm.
And it drops by 1 volt here.
Just negative 1.5.
So it's negative 1.5. Now I go from here to here. It increases by 1.5, right?
Mm-hmm.
So negative 1.5 plus positive 1.5 equals 0.
Yeah.
So if I add up all the delta V's as I go in a loop, I get 0. And that's because of the fact that if you integrate the electric field around a closed loop, you get 0. That's because the electric field is conservative. And this statement is called Kirchhoff's loop rule, that the sum of the voltage drop in any closed loop is 0. And that's very obvious if you have two resistors in parallel. So let's look at the case where you have two resistors in parallel. In fact, the two resistors in parallel are going to give me the second of the two Kirchhoff's rules. That loop rule and the second one I'm going to come up with here are going to be very important when we analyze circuits when the resistors are in either series or parallel. Okay, so let me draw my circuit. R1, R2. There's my power supply voltage. It can be a battery, whatever, but it's a constant voltage source. They're in parallel, so let's pretend this is 0 volts and this is 1.5 volts, just to put numbers in. Okay? This point's 1.5 volts. This point is 1.5 volts. This point is 1.5 volts. So are these points. Then everything over here is 0 volts. And so the voltage drop across each resistor is 1.5 volts. They're in parallel. That's what you expect. So the voltage drop across each one of them is 1.5 volts. So that means that delta V1 equals delta V2. Now let's think about the current. Let's think about the electrons. The electrons are going to come around and they reach this node. What's going to happen? And just think of water flowing through a pipe. Some of it's going to go this way and some of it's going to go this way. If this is the total current I, then some of it's going to go here and some of it's going to go here. Just think of water flowing through a pipe, right? And you reach a T. Some water is going to go one way and some water is going to go the other way. And so then my current, my total current is going to be I1 plus I2. But we know Ohm's law. We know I is delta V over R. So then this is going to be delta V1 over R plus delta V2 over R, or 1 and R2, sorry. But these two delta V's are the same. They're the same as the power supply voltage. So I'm going to rewrite this. What's my goal? I want to replace those two with a single resistor that gives me the same current. The delta V sub S's cancel, and I get 1 over R equivalent equals 1 over R1 plus 1 over R2. They add as reciprocals. And so R parallel is equal to R1 to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1 plus dot, dot, dot. The whole thing to the minus 1. And what happens is this resistor value is smaller than either one of these two. And that's because the total current through the batteries is some of these two currents. The amount of current going into this node equals the amount of current going out of the node. And yeah, that's an important idea. That's from conservation of charge. Okay. That whatever goes in comes out. The sum of the currents at a node is 0. The sum of the current at any junction is a 0. Another way to say it is whatever goes in comes out. That's Kirchhoff's junction rule. And so the junction rule, or the current rule, along with the loop rule, will be used next week to solve some more complex circuits. So just to review, these are the equations for resistors in series and parallel. The form of the equations here are switched from those for the capacitors. Please be aware of that. So I'm going to stop here. Next time I'm going to do an example just like I did for the capacitors. Okay? And I'm going to do it. I'm going to do a demonstration too. And I'm hoping more people show up because I'm going to ask questions in a demonstration. Okay. I want to say a thing about electric current, and then I'll stop. You all know the electric current can be dangerous. Okay.
Yeah.
How much current can kill you? There's a document on Canvas called a fatal current, which will tell you how much current will kill you. If you can get 75 milliamps through your body, that'll kill you. If you get this much current through your body, it's not a lot of current. That'll kill you. That'll make your heart, it'll get you into your heart in fibrillation. It'll get your heartbeat out of whack. Okay? And that'll kill you. You will start feeling something, sensations at around 10 milliamps, or maybe a little bit less. I don't know if it ever, I mean, I was always curious as a little kid, so I don't know if you ever did this with a 9-volt battery. You take the 9-volt battery and put it on your tongue. Have you ever done that?
I have not.
Okay. Well, you'll feel it. You'll feel the current on your, because between the 2 points on your tongue, the resistance is low, so you'll feel it. Kids do that. I mean, I don't know if kids don't do it now, but when we were little, we were, that's how we would test if the battery was good. If you got zapped by it, then you know it's good.
I mean, I know that one thing they do now, I don't know about 9 volts, but I know with some batteries, they make them taste really bad so that kids don't eat them.
So you can't do
put
it?
them in their mouth. Yeah.
Oh, okay.
I mean, I don't know if you can test the positive and negative ends, but I think it's just in general the battery tastes bad so that like little children don't eat them.
Don't eat them?
Yeah. And swallow on them or choke on them and such. So.
Yeah, that's a concern. You have kids choke on them. The 9-volt battery, because the terminals are real close to each other, you could test them by just putting your tongue on them. Anyway, but you feel a sensation. It's milliamps. You get to a point, and I forget the number, where you touch a wire and your muscles contract and you can't let go. And the only way is for somebody to come, for somebody to come up and unplug it and not touch you. A lot of times the first reaction that helps someone who's being electrocuted is to go up and grab them, grab their arm, and then you're going to get electrocuted too. You actually turn off the source. Okay. When you get to higher currents, though, like an amp, what will happen is your heart, instead of going into fibrillation, it'll stop. And if someone's able to rescue you, you can actually survive that as compared to the 75 milliamps because your heart stops instead of going out of whack. Of course, though, the problem is when you get to about an amp or higher, you start to cook. You'll start getting burns because that energy is going to be converted into heat. So
how do people survive lightning strikes? Because I know those are like very a lot.
Yeah, it just depends on how much charge is dumped into you. I mean, I remember in the 70s there was a golf tournament. I think it was in Chicago. I'm from Chicago, and it was a pro golf tournament. I think Lee Trevino, Lee Trevino was there. He was outside golfing in the middle of a thunderstorm, and he got zapped. He survived it.
Wow.
You don't want to play golf on an open course when there's a thunderstorm. That's a bad idea.
Yeah.
Because you're a lightning
Especially
rod.
with your metal poles. Yeah.
So we put together. Normally I do this live in class. It's much better when you do it live in class. We put together a little video, or Tyler did, of what happens when you get more than 1 amp go through you. Well, we didn't do it through a person. We did it to a hot dog. So you see that hot dog there? This is on YouTube, by the way.
Yeah.
So we set this up. We're running a voltage through a hot dog. And we measure the voltage and the current. Just to show you what happens to the hot dog. So here, take a look at this video.
Experimental demos. In front of you, we have the dangers of electricity. There is a hot dog made to represent your finger, or you, and which will be running electricity or current through. On the left is a variac, so I'm going to adjust the AC voltage up, and we're going to measure it on the left in amps, and the voltage on the right. So if we follow this, the current, it goes through and is done in series, and the voltage is measured in parallel across those. So we're going to turn it on, and keep adjusting it. 40 volts, I'm already getting almost 2 amps of current. I can see the top of the hot dog already bulging out. It's broken apart. And we have lots of steam.
You can see the bubbling there.
Yeah. Oh, and I can see the steam on the right.
Yeah. So that's how quick it is.
Yeah.
The only thing missing is the smell of the cooking hot dog.
Yeah.
Okay, so anyway.
Hi everyone.
So I just wanted to show you that video, and if you get a chance, please read that fatal current demo. So the labs we do, the voltages are very low, so you're not going to get electrocuted.
Mm-hmm.
But if you're doing stuff around the house, you want to think about being careful. Always have one arm behind your back when you're working around electrical, so you don't get zapped. It's dangerous. Okay, so I'm going to stop here.
All right.